Good morning. So today we will be discussing one exercise given in the textbook. So the principle or the learning outcome of this exercise is that to estimate the average velocity of a Newtonian fluid in a horizontal pipe flow. Okay, so this fluid being considered is a Newtonian fluid and it is flowing through a horizontal pipe. Actually, a kind of problem we have done, or we have done a derivation in the form of derivation of Hagen-Poiseuille equation. So now this can be considered as an extension of that particular problem. So the current problem statement is that for turbulent flow of Newtonian fluid in a horizontal pipe, the velocity profile is established in the following format. That is, velocity is equal to maximum velocity into 1 minus r by r to the power 1 by 7, and we are required to obtain the value of V average. Okay, means average velocity. So now let me just explain the actually notations used here. That here this V means Vxr, means see velocity in axial direction at location r. So this r represents the r dimension, radial dimension, whereas this capital R means the radius of the tube. So just actually I am giving that explanation. Let us say we are considering a tube of radius r, means let us say this is at location 0. Here it is radial location 0, means at the center. So upward it is r length, r height, and downward as r height. And of course, actually if we get a cross section, actually we are getting a circular disc kind of thing. So now if we think about the area of flow, is that is actually cross sectional area of flow will be pi r square. And now you see in the problem it is said that at location r, means okay, any arbitrary location r, it is here, any arbitrary location r. So velocity of fluid which is at a location r, its velocity in axial direction is given by this expression. And of course similar expression we have got for laminar flow. So now it is just this extension only. You can note that actually see this power is the difference. Okay, so based on that power, actually I think we can see a difference in the expression for this V average. Now for this case, okay, now you see this expression is given in the form of that velocity is a function of maximum velocity, and from the earlier discussions we know that maximum velocity happens where r is equal to 0 or at the center. So we are showing at V maximum here, and at r is equal to r means at the radius or interface with the solid surface. So this velocity is 0. So velocity is 0 here and 0 here, whereas velocity is maximum here. And as compared to this laminar flow regime, this profile will be quite flatter one, whereas actually in case of laminar flow we will be getting a curve like this. Okay, now one particular thing let us note here. You see at location r, velocity is given by this V. So now throw a strip of thickness delta r, how much fluid will be flowing? That will be the area of this strip multiplied by the velocity, means area, cross sectional area of this strip into velocity. So velocity here is given already, and cross sectional area for this strip, okay, will be actually see peripheral length or periphery of this ring, which is basically 2 pi r multiplied by its width. So now we are writing it as a delta r. Okay, now you see delta r, when we write delta r, then we can say that what is the total flow happening here, means we are required to divide everything into such similar annular rings, and we are means you see integrating the liquid or fluid flowing through it from 0 to the outermost radius. Now that whenever we are estimating these values in terms of, you see, delta r, then we are actually, see, summing it up. However, the same thing we are going to do by integration. So now we will be writing this equation in differentiation term. So now you see average velocity is what? Average velocity multiplied by the cross-sectional area gives you the net amount of fluid flowing through the tube. So the net amount of fluid flowing through the tube is basically, see, this velocity. This V means actually, see, this Vxr is in axial direction at location r, multiplied by this area of this ring. Okay, now since we are talking in differential form, okay, then we will be writing it as dr, and to get the know the total value, we are integrating from 0 to r. Okay, so 0 to r means from center up to the outermost location. So now we are writing it as a integration expression. And however, at the same time, we know the cross sectional area is pi r square. This, for this also we can write it in integral form, and we can get this final expression, or we can write directly from our prior knowledge. So we get this expression for V average means total amount of fluid flowing through the tube divided by the cross sectional area. Okay, so now minor, you can call it means rearrangement of these terms and simplification. We get this, actually pi's are getting cancelled and 2 is being constant, we are taking it out. So what is remaining inside the integration sign is actually Vr dr. Okay, velocity into radius. So now for this velocity, we are substituting the expression given in the problem. So 2 into Vmax, again is constant. Vmax is a constant value, so we are taking it out. So 2 into Vmax by r square, only what is remaining is this, you see, term dependent on r, means position, term that is dependent on the position, that is remaining. So that is for V, and then r dr remaining. So now for integrating this expression, we are just, you see, transforming the variable. So earlier this was written in terms of r, so now we are interested to write it in terms of x. So we are assuming that whatever is here, this variable's name I were giving as x. So if we simplify it, then it will be saying that, okay, r is, means your variable r is pipe radius multiplied by 1 minus x. And if we differentiate this particular expression, then we get dr is equal to minus r dx. So when we change the variable, then the limit also changes. Earlier limit was from 0 to r, means from center to outermost position. Now since, you see, x is dependent on r by r, so at center this r is 0, 0 by r means actually at center x becomes 1, and at outermost position 1 minus capital R by capital R, so they get cancelled out, it becomes 1, 1 minus 1 means 0. So now this limit will be changing to 1 to 0. So this, with this substitution of the changed variable, what we get, V average is equal to 2V max by r square multiplied by this integration from 1 to 0. Now this is that, you can just see it, x to the power 1 by 7, where from it is coming, this one, x to the power 1 by 7. Okay, then this is the expression for r, small r, and then this is the expression for dr. Okay, then this quite simple, actually you can call it manipulation and simplification. Both the r's are getting cancelled, so r square is vanishing here, so 2 into Vmax is remaining, and then only the terms which are dependent on x is remaining inside the integration sign. So x to the power 1 by 7 and x to the power 8 by 7, and it is minus 2Vx because of this minus sign is there. Okay, and it is now dx. So it is being now broken down to two integrals, then integration is done. So after being it is a finite integral, so then we are putting the limit from 1 to 0, and this is the integration of 1 by 7 is basically x to the power 8 by 7 divided by 8 by 7, and for this other one x to the power 8 by 7, this is x to the power 15 by 7 divided by x to this is 15 by 7, and okay, we can simplify in this way. Now this sign, minus sign was there, so we want to eliminate this minus sign, so then therefore we have changed the limit. Earlier it was from 1 to 0, so when we are eliminating it, removing it, then this limit gets altered from it is now 0 to 1. So 2 into v max 7 by 8 x to the power 8 by 7 minus 7 by 15 x to the power 15 by 7. So now after doing it, actually see substitution is quite easy. So whenever x is equal to 0, these terms vanishes, so we are ignoring that. When x is equal to 1, we get again, you see, x to the power 8 by 7 means whatever is there, whatever power will be there, that term will be vanishing, only these coefficients are remaining. So 2 into v max multiplied by first coefficient minus second coefficient, so this turns out to be 2 into v max divided by 14 by 120, and that is 0.817 into v maximum. Okay, so now actually this gives us the relationship between average velocity and maximum velocity for turbulent flow of Newtonian fluid in a horizontal pipe. So now it means actually see this average velocity is 81.7% of the maximum velocity. So maximum velocity happens at the center. Okay. Now just for actually see to understand it better, you can see to make for a comparison, you can compare it with whatever we had done earlier. Okay. Then there we had seen that actually in case of laminar flow, in the same pipe arrangement, this ratio was 50%. Means when the flow is laminar, then this ratio is 50%. So means V average by V maximum is equal to 0.5 in case of laminar flow. Okay. So now actually what we can say that is by just doing this simple exercise, what we have learned and what we can remember, or what we can say that what we can apply in future is that how to compute the average values of the velocity from the known velocity distribution. And of course this we had done for 1D flow, one dimensional flow. The flow is happening only in x direction. So now this idea will try to extend for some other flow arrangement as well. So that's all. It is a short video just to help you out in solving the example. Thank you.